recording. Okay, Bismillahirrahmanirrahim. So today we are going to continue with the topic halogenoalkane. So last time we've already looked at the physical properties and the reactivities of the different halogenoalkanes. And the next one is supposed to be the reaction of halogenoalkanes with aqueous silver nitrate. But I will skip this for now because I will go back to this slide later on after we have confidently covered the mechanisms. So I would like to skip that to the next learning objective, which is the production of halogenoalkanes. How can halogenoalkanes be produced? When I started this topic, I mentioned that halogenoalkanes are basically just alkanes with their hydrogen atoms substituted. That means halogenoalkanes are derivatives of your alkanes. And we saw this reaction called the free radical substitution of alkanes, which resulted in the production of halogenoalkanes. And then in the second functional group that we covered, which was alkenes, we also saw that alkenes undergo electrophilic addition reaction to form a halogenoalkanes. Whether you add the element in its standard state, like chlorine, Cl2, or bromine, Br2, or you add the hydrogen halide, HX. So that can be HCl, HBr. Usually, these are your HCl in its purest form, which is in a gas state, HCl. Okay. Okay. And the third one is something that you have not come across, but you will be learning that. That's something new for you to learn today, and will also be revised again in the next topic, which is topic 16, hydroxy group. Okay, so alcohols can actually be your starting material to produce a halogenoalkane. Okay, in this case, the hydroxy group OH will be substituted with a halogen. Right, so there are a few types for the reaction of alcohols. There are a few types of reactions that you can use. Okay, so these are the three reactions that I've just mentioned, right? So the first one, free radical substitution of alkanes. You don't have to copy this down because this is just the mechanism of a free radical substitution, which is something that you have learned already. But I would just like to remind you that this reaction is a substitution reaction where one or more hydrogen is being replaced by a halogen atom, by one or more halogen atoms. Okay. So you will notice that whenever you have a saturated compound or saturated molecules, they tend to go through a substitution reaction rather than an addition reaction, because saturated means they're already full. You cannot add anymore, but you can swap or replace them. Okay. The next reaction is the electrophilic addition to alkenes. Again, you don't have to copy this down because it's already in your notes. Is given. You're given the general equation. So the first reaction is when you use hydrogen halides. Hydrogen halides is HX, where X is your halogen. It can be chlorine or bromine. Well, those two are the ones that I mentioned in your syllabus anyway. Okay, so this is showing you if you have an unsymmetrical alkenes, you can produce two possible products, one being the major and one being the minor. Again, I will not go into details, but what I want to emphasize on is that the hydrogen halides will only be added across the double bond. So if you have an alkene that contains like 20 carbon atoms, the reaction will only occur at the reactive site, which is your functional group, where your C double bond C is, okay? So one hydrogen atom will be attached to one of the carbon atoms in the double bond, and the halogen atom will go to the other carbon atom. Okay, same case if you react your alkenes with halogens instead of hydrogen halides. Halogens, they exist as a diatomic molecule, F2Cl2Br2I2. So naturally, you will be adding two halogen atoms across the double bond. Okay, so this reaction is a greater or a better reaction than the reaction of your free radical substitution with alkanes, because free radical substitutions is crazy. Radicals are reactive. They will continue in what we call a chain reaction. We cannot stop it. If there is a specific product that we desire, okay, a desired product, we cannot control the reaction. Unlike electrophilic addition, I know the products that I'm getting, so I can just collect that product, and I know that there will not be any other side products from that reaction. Okay, unless of course if you use a symmetrical and unsymmetrical alkenes, in which case you will have two products which may not be easy to separate, especially that they are isomers. Okay, so they're not as easy to separate. The next reaction is the greatest, I think, okay? The best if you want to make a halogenoalkanes, because they can target the position, okay? So if you want to attach your halogenoalkane here at your hydroxy group, that's where your halogen will be placed, okay? So if you put your OH here, again, that's where your halogen will be placed, okay? So this is a substitution reaction. The hydroxy group, the OH bond, since that's the functional group, will be replaced with the halogen. Okay, the first type is the reaction of alcohol with hydrogen halides, so HX, where X can be HCl gas or HBr. Now, the problem with hydrogen chloride gas, not HCl hydrochloric acid, is the hydrogen chloride gas or the hydrogen bromide in the purest form. The problem with them is that we cannot store it in the bottle because hydrogen chloride gas is a gas. The only way you can feed or add this reactant together with the alcohol is by making hydrogen halides on the spot. We call this in situ. You make it inside the reaction mixture together with the alcohol. So how do you form a hydrogen bromide, for example? To form a hydrogen bromide, you would add potassium bromide with sulfuric acid as your catalyst or phosphoric acid as your catalyst. Okay, so this is actually a group 1 metal bromide. So you can use potassium bromide or sodium bromide. If you want to produce hydrogen chloride, you would use potassium chloride or sodium bromide with sulfuric acid or phosphoric acid. Then in that reaction, in the same reaction mixture, once you form your hydrogen halides, it will react with your alcohol immediately. All right, so that's the idea of in situ. You will come across this word again in the future. Okay, so in situ means it is produced together with the reactant, the other reactant. Okay, so what happens is that your halogen will substitute your hydroxy group, and then you will form a halogenoalkane. The other product would be water. That's one type. The second type, if you don't want to produce hydrogen halides on the spot or inside the reaction, you can just use a phosphorus halides. We call this a phosphorus halides. PCl3 specifically is called a phosphorus trichloride. So PCl3 is readily available. You can just throw it and mix it with your alcohol. Again, for the same substitution reaction, your hydroxy group is being substituted with a chlorine atom. Okay, now even though there are 3 chlorine atoms in PCl3, for the alcohol, there's only one functional group. Only that hydroxy group will be replaced. This hydrogen or any other hydrogen will not be replaced by the chlorine because they are not the functional group. Okay, so don't think that, oh, I've got 3 chlorines. That means I have to sub in 3 chlorines into this starting material. No, only the functional group will be replaced. So that's why you have a chlorine here. The other product would be a phosphorus acid, H3PO3, which is not phosphoric acid. So you don't need a catalyst for this. You just need to heat up the experiment. Okay, even better is using PCl5. PCl5 is a solid at room temperature. So this one you don't need to make in situ. You just order it from a supplier. It comes in a bottle. You add it straight away to your starting alcohol. Okay, so then same thing. Your hydroxy group will be replaced by a chlorine atom. Since there's only one hydroxy group, only one chlorine atom will be, only one hydroxy group will be swapped or substituted with the chlorine atom. The other products you would form would be HCl, hydrogen chloride gas. It will be in the form of gas, not in the aqueous form. You will see this as white, steamy fume. So usually, if that reaction involves an observation, you can use it as a test, right? So if you throw in PCl5 with an unknown compound, and then you see white steamy fume, and you test that white steamy fume is a hydrogen chloride gas, then you can conclude that maybe, okay, maybe you don't conclude it yet, okay, that maybe a hydroxy group is present in that unknown compound. Okay, so this reaction can be used as a test or confirmation of the presence of hydroxy group. So that's nice. PCl5, you don't need to heat it up. It happens at room temperature. So this is a good way, a good reaction to produce your desired halogenoalkane, right? The last type of reaction for alcohol, it goes through the same mechanism because it's still a substitution reaction, but the only difference is that you are using a different reagent. Okay, PCl5 is a phosphorus pentachloride and it's in a solid form. SOCl2 is Socyl 2. The name is, if I can find the name of Socyl 2, sulfur dichloride oxide. Usually I just refer it to Socyl 2. It doesn't mention if Socyl 2 is a solid or a liquid at room temperature. Okay, but there's no condition. It works at room temperature. You don't need to heat it up. But this reaction is the greatest because, so there's the chlorine and then the chlorine is substituted because of the product. Hydrogen chloride is in the form of gas. Sulfur dioxide is in the form of gas. So if you let these two gaseous products evaporate, that leaves you with your desired product. You don't have to do anything to it. So Socle 2, if you're looking for if you get a few options to choose from to produce a halogenoalkane, choose Socle 2. Okay, because you have other side products, but they are in gaseous state. You can just let them evaporate and you will get the halogenoalkane that you want, right? Whereas like the others, you have water, you have phosphorus acid, and then you have POCl3, which I imagine would be liquid. Okay. Okay, so this is something new for you. You have to memorize the reagents. You have to memorize the condition. Okay. The side products, yes, sometimes you have to memorize it too, especially if they want to ask you to write down the balance equation. All right. Okay, moving on to the next one. Okay, so this is just the overview of the reaction that that can result in the formation of halogenoalkanes. Next, we want to look at the reactions of halogenoalkanes. Okay, the mechanism for halogenoalkanes is called the nucleophilic substitution reaction. There are two types, SN1 and SN2. Recall that primary halogenoalkanes will tend to go through SN2 and tertiary halogenoalkanes will tend to go through SN1. So I will give you the explanation later on. What about secondary halogenoalkane? Well, it can go through a mixture, can be SN1, can be SN2, or mix. Some goes to SN1, some goes through SN2. Okay. Right, reactions of halogenoalkanes, there are two types. The first one is the substitution, because halogenoalkanes are a saturated molecule. They contain all single bonds. So it's a substitution reaction. And the attacking species is the nucleophiles. Previously, for double bond, you saw that it was an electrophilic addition reaction. So electrophiles are species that accept lone pairs. Nucleophile are species that donate lone pairs. So what is the criteria of being a nucleophile? You need to have a lone pair of electrons that you can donate. Okay, right. The definition of substitution, the halogen atom is being swapped with another atom or groups of atoms. I'm sure you all know that already. Electron pair donors is the definition for nucleophile. These are some examples. OH minus hydroxy ion is a nucleophile and the lone pair of electron comes from the oxygen atom. Ammonia, which is neutral, can also act as a nucleophile because there is a lone pair on the nitrogen, not the hydrogen. Okay, this one you already know, you have learned in topic 3. Cyanide ion is something new for you. This is called cyanide ion. And it actually consists of a triple bond, C triple bond. And the most important thing is the lone pair of electrons is on the carbon, not the nitrogen. Okay, so it's easy to get this wrong. Okay, because you think, oh, nitrogen has lone pairs, so it must be the one that is coming from the nitrogen. No, because the lone pair of nitrogen is actually already used here. Okay. No, it's not used. It's not used. It's there, but it's not the one that we use for this mechanism. Okay, why is it important to identify where the lone pairs is coming from? Because these nucleophiles will donate their lone pairs to a certain atom, which I will show you shortly. So whichever atom that lone pair is being donated to, they form a new bond with that atom. So it will be a new bond between carbon and another carbon, for example. Okay, so if the lone pair comes from nitrogen, it has to be the nitrogen that is forming a bond with the carbon. And that's not the case for this reaction, right? Okay, that's cyanide ion. For water, you know that the lone pair belongs to oxygen. So that's not too worrying. Okay, the only thing that you need to be careful is the cyanide ion. It's so easy to think that the lone pair comes from the nitrogen, but for this reaction, it comes from the carbon. Okay, now because they are electron pair donors, they are relatively electron-rich species. Okay, so you would imagine them to attract electron-poor species. Before we move on to the next part, I just want to tell you that there are two types of mechanism. SN1, which is usually for tertiary halogenoalkanes. SN2 is usually for primary halogenoalkanes. What about the secondary halogenoalkanes? Well, they can go through a mixture of both SN1 and SN2. Okay, so there's no fixed rules for this secondary halogenoalkanes. Okay, next, looking at the theory, okay, the carbon halogen bond, if I just use one example, the easiest one would be, a chloroethane. We know that the electronegativity of the chlorine is relatively higher than the electronegativity of carbon. So this carbon-chlorine bond is a polar bond. Because there's a polar bond, they have dipoles, okay? Delta plus, delta minus. So between this delta plus and delta minus, because these are the region that will be attacked by the nucleophiles, the nucleophiles, which is electron rich, will be attacking someone who is electron poor. And usually the one with the slightly positive charge is the electron poor region. Okay, electronegativity of chlorine is very high, so that means it has pulled the electron density that they were sharing closer to itself, increasing the electron density of the chlorine atom whilst decreasing the electron density of the carbon atom. So you just think about it as something that is electron rich, something that is negative, attracted to something that is positive. In this case, it's the carbon. Okay, so halogens have a greater electronegativity than carbon, and the slightly positive carbon is thus open to attack by nucleophiles. Okay, so I will show you the mechanism first, and then I will let you copy down. After this, there's some explanations to it, which is on the second slide. I'll move on to the second slide later on, but I want you to follow my drawing first, okay? Right, so what happens is that I am going to, so this is an SN2 mechanism. S stands for substitution, N stands for nucleophilic, 2 stands for 2 reagents. Okay, this SN2 is not so much of your concern right now. It's more relevant for when we look at the rate of reaction later on. Okay, the 2 reagents, I will talk about that shortly. Right, so where is the Okay, so I'm going to use primary halogenoalkane, which is what's on the next page? Bromine. Okay, so I will use bromine. Bromoethane. Just the easiest example. Okay, and you have to label your carbon, which is delta plus, and your halogen, in this case, the bromine, which is delta minus. And then your nucleophile, in this case, is your hydroxy ion, and you must draw the lone pair. Without the lone pair, the mechanism will not make sense. Okay, what are you moving, right? So first, what's going to happen is, okay, the reason why it's called 2, because there are 2 reagents here, okay? The first reagent is your bromoethane. The second reagent is your hydroxy ion, which is your nucleophile. So that's where the SN2 is coming from. The second type, which is SN1, that means there's only one reagent. Okay, I'll talk about that later. Okay, so what happens is that the electron-rich nucleophile, which is your hydroxy ion, will attack and donate its lone pair of electrons to the electron poor carbon, the slightly positive carbon. So you can imagine that a bond will be formed here. A carbon-oxygen bond will be the new bond that will be formed. Okay, so that means your carbon will have 5 bonds. One of the carbons need to break. If you look at the bonds around this carbon, there's a carbon hydrogen, there's a carbon carbon, and there's a carbon bromine bond. So by right, it has to be the weakest bond to be broken. And the weakest bond among these 4 bonds that I've just highlighted is the CBr bond. Okay, so the carbon bromine bond will break and the electrons will go to bromine. So this fits with the fact that bromine has a higher electronegativity value. Bromine has a stronger attraction for the bonding electrons. So now both the bonding electrons will go to bromine. Okay, next will be a transition state, which is an intermediate, where you would draw it like this. So this is the original bromoethane. Okay, so we draw it as a dotted line to show that it is in the process of breaking in the case of CBr and in the process of making in the case of hydroxide ion. Okay, so you can see that there are 1, 2, 3 and a half and another half bond. So that dotted line is showing you in the process of bond forming, and the blue dotted is showing you bond breaking. Okay, don't forget the negative charge of the hydroxy ion. Some drawing, you will see that they write the negative charge outside. It doesn't matter. Okay, so transition state is usually drawn in a square bracket. And that symbol is showing you that it is a transition state symbol. What a transition state means is something that is temporary, intermediate. Okay, what else do I want to? Okay, so in this stage, there is no arrow being shown. You go straight to the product, which is your new product, which is an alcohol. So we've seen just now, right, that you can from halogenoalkanes from alcohol, you can also do the reverse from halogenoalkanes to alcohol, from alcohol to halogenoalkanes. Okay. So carbon oxygen bond is the new bond form. Don't forget your other product, that bromine, that partially negative bromine will now become a full negative charge of bromine. So you get an ethanol from bromoethane. Usually these hydroxy ions come with a counter ion like sodium hydroxide. So in your product, you will get a sodium bromide, right? If it comes with potassium hydroxide in the product, you will get potassium bromide, right? So I want you to copy this drawing first. And then, add one more thing here. Attack of nucleophile. Attack of nucleophile from the opposite side of halogen. Why don't the nucleophiles attack on the same side of the halogen? Because nucleophile is a negative charge, electron rich. Halogen is slightly negative, which is also an electron rich. So what happens if you bring them close is that they will repel. Okay, so this attack has to be from the other side. So this is mostly about the steric factor, which is not your concern now. Okay, so if you haven't finished copying this down, you can always go back to this later. The explanation comes on the next slide. So I will change it. Okay, so right, I forgot to add slow process here, which again is not your concern now, but it will be relevant when we do rate of reaction later on. So the explanation is here. The nucleophile hydroxy ion donates a pair of electrons to a slightly positive carbon atom to form a new covalent bond. And at the same time, the carbon halogen bond is breaking. So here you can see clearly that the hydroxide is attacking from the opposite side. Okay, this is showing you the 3D shape. But in the exam, usually just show the normal drawing, the one that I draw previously. Okay, this results in the formation of intermediate at transition state. This transition state is very, very unstable because carbon with 5 bonds, you can't have that, right? So it's just a temporary, very quick stage, and then you move on to the product. So the halogen atom takes both the electrons in the bond, so this is a heterolytic fission, and leaves as a halide ion, which is bromine, with a full negative charge. So students always forget, they still write down the slightly negative charge. Okay, once bromine has obtained the electrons, it is now fully owned by them. They should have a full negative charge. Okay, so we have about 3 minutes left. I'll leave it on this slide for you to copy. Please let me know if you're done copying.